This is joint work with my colleagues from Technische Universität Darmstadt and University of Duisburg-Essen in Germany. And I'm going to present K-Miner, which is our new static analysis framework for analysis of the Linux kernel. And actually, to the best of our knowledge, this is the first framework that enables inter-procedural data flow analysis for kernel code. So you might ask yourself, why static analysis? Why static analysis framework? So in the beginning, there was code, which was written by humans, and therefore it was bad. To be fair, kernel code typically contains less bugs than user-level code, but also in the kernel context, these bugs are typically more critical because the kernel runs with higher privileges, and therefore any bug that affects the code can have an effect on the entire system. And examples of such memory corruption vulnerabilities are use after free, double free, use after return, and so on. We have a detailed classification on this in the paper. And to obtain machine code from the source files, typically these are compiled or transformed by the compiler into machine code, which will pass on the bug into the binary. And then the binary will be executed by the hardware at runtime. Now, user space adversary can, at runtime, deliberately trigger this bug to corrupt the operating system through calling system calls and exploit the operating system to gain access to the entire system. Consequently, people are trying to find these bugs in multiple ways, and one of the ways of finding such bugs could be through dynamic analysis at runtime. So you would scan the system during the runtime and find if there's a bug. The problem of these approaches is that they have to, in order to really catch all the bugs, they would have to scan every single individual input that is provided. And since this is infeasible, they typically start from known error conditions and work their way from there, and consequently might step over bugs by missing inputs. And in contrast to this, static analysis reasons about the abstract program in the form of source code, and it hence does not have to actually scan the entire input spectrum, but reasons about this abstract description. And this is what we do. So how does data flow analysis work? In particular, it uses graphs to reason about the program behavior. So if you take the simple example on the left, we can build a series of graphs to describe it. For instance, in this case, the call graph is a simple example. The main function calls the printf function, and hence in the call graph we have an edge from main to printf, very simple. The control flow graph, for instance, has edges for indirect jumps, and the nodes of the graph depict the basic blocks of the program. Then we also have graphs like the pointer assignment graph, where we track pointer and abstract memory objects. And we might also label these objects and pointers to them with their allocation sites and the type of the allocation and so on. In this case, we have an edge from the stack object A to P because there's an assignment from the address of A to P in the program. To capture the conditions or the constraints behind these assignments, we can use a constraint graph. So the edge from the abstract object to object P in this case would encode that there is a condition, namely that A has to be non-zero for this assignment to happen. And last but not least, we can use a value flow graph. This is a very useful representation because it combines the assignment of pointers and abstract memory objects with the control flow of the program. And in this case, we have a phi function, which is just an artifact of the single static assignment form that the compiler uses to construct this kind of graph. Because in this case, the graph edges actually represent value flows. So if we have two edges that go into one node, we cannot really meaningfully compute return values. So the phi function is a kind of helper construct to always select the correct value. Yeah, and we can actually use these graphs to find bugs. So for instance, we can utilize the value flow graph that I showed you in the slide before to find the double-free vulnerability in this program, because the program just frees any non-null allocation twice. And this is also reflected in the value flow graph. So if we mark the allocation function as a source and the free function as a sink, we can conduct a simple source sink analysis, and we'll find that yeah, the allocations are basically flowing to two sinks. So there exists a path in the program that reaches two sinks, and hence the program is buggy. While all this seems rather simple for, or rather easy for such simple examples, when we scale this up to real-world programs, the complexity of the analysis rises dramatically. So this is because the number of paths in the program actually rises exponentially with the input size of the program, and so the number, or these graph sizes, they typically explode when you give it bigger programs. In addition to that, we may also want to investigate additional properties. For example, we want to have an inter-procedural analysis, which means that we look at the behavior of the program with respect to multiple functions and spanning multiple functions, not just a single function. We might have to look at field-sensitive analysis, so not treat two different fields of a struct object as one object, but rather as distinct objects. And finally, the analysis can also depend on some kind of external state, like the parameters that we pass in and the memory context that is already established within the program and so on. And all of these properties are actually needed to reliably detect memory corruption, which is what we want to do. And unfortunately, this presents us with huge scalability challenges. So when we looked at the related work, we found that to the best of our knowledge, none of the tools that exist can actually do what we want. Namely, Smatch, Sparse, and Coccinelle are very popular tools for analyzing the Linux kernel. However, these are text-based tools. So they scan the input files of the kernel, and they are limited to inter-procedural checks. So this means per file and even per function. Last year at Usenix, Unidal presented API-SAN, which is a framework to detect semantic errors in a Linux kernel. However, they focus on API usage errors. So when a function is called with the switch parameters, for instance, or wrong parameters, and a null value is passed in the wrong way, and so on. And they cannot conduct any inter-procedural data flow analysis. And then lastly, there's the effect-based analyzer, EBA, and they focus on synchronization and log errors. While there are some general data flow analysis frameworks for user-space programs, the problem is that we cannot simply adopt these for kernel code, because its workflow and the assumptions that they make about the program are completely different in the kernel. Yes. So in addition to that, the Linux kernel also is simply put really, really big. It's really huge. So the lines of code are always increasing. On the bottom, you can see the versions, and it's rising dramatically. And also, if this trend continues, it keeps growing in the future. And we wanted to have a framework that can somehow deal with this amount of code in a reasonable way, and also ensure that we can conduct analysis in future versions as well. So this is the contributions and challenges that we faced. In particular, KMN has to tackle a number of challenges, and the main contributions are that we analyze the code of the Linux kernel based on the LLVM intermediate representation and enable a data flow analysis for this large code base. We provide a modular framework design that is extensible, and implementing new checkers is actually straightforward. And we already offer several analysis passes that come with the framework and bug checkers that you can run. And finally, there's also a web-based interface for checking the reports that are generated, the memory corruption reports, and scanning them for false positives and going through the code and so on. And it integrates well with the existing tools. Yeah, so the high-level idea to enable this kind of inter-procedural data flow analysis with this huge code base is to partition the kernel. And there is actually a natural kind of interface that we use to do that, namely the system call interface. The system call interface is standardized and rather stable, so there are around 300 system calls in the kernel that provide services to user-land programs. And we leverage this structure in the kernel and partition its code alongside this API in order to analyze each partition separately and using different kinds of analysis. So since the user space adversary has also to use one of those system calls to exploit a memory corruption vulnerability, we can find such bugs in a very similar manner. For instance, the different applications in user space might use different entry points into the kernel, so call different system calls. And if an adversary corrupts one of those system calls using one of the entry points, we figured that we can also conduct the analysis in a very similar way. Yeah, so to corrupt the kernel at runtime, the adversary has to provide a malicious input in such a way that the memory corruption vulnerability gets triggered. And essentially, we try to find that exact point using our static analysis at compile time. Now, the detailed design and workflow of our framework is as follows. We start with the kernel source files and the configuration file for building that kernel version, and both are provided to the compiler, which will generate a bitcode image, so the LLVM bitcode or intermediate representation. And for this, we also have to modify some of the build tools of the kernel. And this bitcode image is then provided to our framework as an input, and the framework then conducts its work in 4 separate phases, which are the pre-processing, partitioning, analysis, and the reporting phase. In the pre-processing phase, we collect and model the abstract memory objects by registering the allocation sites and also the deallocation sites, or freeing functions, and storing all of this information in a database and exporting it for use during the subsequent processing phases. And in the next phase, we partition the kernel alongside the system call API by cloning and pruning the original compilation unit. So this achieves the main reduction in the code size so that we can handle all the huge graph structures that are being built. And in the third phase, then the actual checkers are executed. In particular, you can configure in KMiner the checkers that you want to use. So currently we have, I think, 4 different checkers. And you can also configure them to be run in parallel. And then finally, the results are given to the reporting engine, which will do post-processing and render the results to our web interface. So the user can view all the results and sort them and go through them, scan for false positives, and so on. Our implementation, as I said, builds on the top of the popular LLVM compiler suite, which also provides the necessary intermediate representation and outputs the bitcode format that we need. In addition to that, we use the SVF framework for LLVM, which provides us with the required value flow graphs and also several pointer analysis that we need. And then our bug checkers that we implemented already integrate with the pre-existing LLVM pass infrastructure. So we do have function passes and module passes and so on. And yeah, as I said, we already cover several different classes of memory corruption. In the following, we're going to take a quick look at one of those checkers, namely the use of the return checker, which looks at stack allocations. And we're going to take a look at a very brief example. On the left, you can see a hypothetical, very stripped down version of how a system call might be implemented in the kernel, but it's fairly close to sort of show the idea. So the system call is sysfoo, and it calls some helper function dofoo. And the dofoo function, the value flow graph for the entire thing is on the right. The dofoo function will set up a reference to a local stack object and basically set that to global P in the addX function. And it will only remove this reference conditionally. So there's some condition and if in point 3. And if that condition fails for some reason, then the reference is never removed. So after the dofoo function returns again, this reference is invalid. And there's still a global reference basically to an invalid stack memory object. And an attacker could now take a hold of the reference and somehow exploit it. So how we find such bugs, or how the checker investigates this, is as follows. We can traverse the value flow graph in the forward direction, starting from the local stack allocations, and descend in the value flow graph. So we reach, there it is, until we reach the end. And then we can now flip around the graph and traverse it basically in the backward direction in order to find all the sources. Because since we arrived at the point 6, so the return, let me actually go back. Since we arrive at, it doesn't matter. Since we arrived at node 6, we could see that the reference actually reached at some point in time the return statement in sysfoo. So we know that there is a leak. But in order to find it, we have to traverse backwards and then find two references, basically the local X, which was the original reference, and then the global P, which is the reference that invalidates the program, basically makes it buggy. Yeah, and in this way we can find, basically for checking all the local stack allocations, this checker can find such bugs. In our evaluation, we conducted analysis on using different kernel versions. So in particular, 4 different versions are presented in the paper. And we analyzed all of the about 300 system calls in each version. And yeah, the framework was crunching away at the code and building these graph structures and automatically checking it for several days and even weeks actually for 4 versions. And on average, we had about 25 minutes per system call. So each individual checker took 25 minutes to analyze one of the system calls in one of the versions, and then the average memory consumption was around 12 gigabytes. We found 2 existing vulnerabilities, which were used to conduct privilege escalation exploits previously. And before these vulnerabilities were only found using manual inspection of the code. And yeah, now Kminer can find these completely automatically. We also found 2 new vulnerabilities which were reported to the kernel developers. However, they don't appear to be exploitable at the moment. Yeah, as I said, the framework is expandable, and additional bug checkers can be implemented. These are some more numbers, but the details are also given in the paper. I will show you some screenshots of the web-based overview of for one of the system calls. So this is for one of the system calls. You can see that you have the 3 checkers running, and this is the detail view where you can see what's going on, like which memory objects are being traced and so on. Where's the problem exactly? And then this is what the overview for the checker list basically looks like. You can go in and select one of the files where the framework thinks that there's a bug, and you can directly jump into the code. So you click on the link, you go to the code, can investigate it and see if it's false positive or not, and then check it. Yeah, we released our framework as an open source implementation, and feel free to check it out. I'm open to take questions.
Please come to the microphone if you have questions, and please state your name and affiliation before you shoot your questions. Thanks.
Hi, I'm Nathan Burrow from Purdue. I was wondering if you could comment on the false positive rate that you observed, since you mentioned that issue many times.
Yeah, so we do have a number of false positives, like any other static analysis framework as well. And it's, yeah, I mean, naturally you have to look through the reports and scan them and inspect them manually. We thought about building something like an automatic rating system in API side that did something like that, but we didn't do it for the paper, so this is part of our future work.
Okay, thank you.
All right, since we're kind of running out of time, let's thank our speaker one more time.